In business, every day you have a decision to make, and making those decisions can be very complicated. You have a lot of different variables in front of you, and you might not have all the information that you need. But what if I told you that there's tools in order to help with that decision making space and deliver the outputs that you want? I want to talk about today about a machine learning model called XGBoost. I want to show you how I've used it with real data, financial data, to help drive decisions in this space, specifically procurement decisions. The example I'm going to give is trying to track prices of steel and where it's going. That helps you in negotiation. It helps you understand where prices may lead. Say you're building an item and you know what raw components go into it. At least you can begin to better understand the material prices and where they're headed in a given situation. And you can use it for a variety of other things as well. The version we're going to use is going to be trying to predict a continuous variable, dollars. So we're going to use regression to measure the output. But you can also use this to measure things like categoricals. Say you're trying to bid on a contract and understand whether or not you're going to receive that given bid, given X different parameters. Well, now you can run through different scenario planning to begin to understand what your bid should come in at, or what different elements you should add to your contract to ensure that you get a given bid. It's a very powerful tool that provides a ton of insights. So without further ado, let's go ahead and jump into the script and a few extra areas to begin to understand how XGBoost, a gradient boosting model, helps achieve this answer. I want to start with looking at the data that we're planning on using. So specifically, we're going to be looking at this Excel spreadsheet right here. And in here, you can see different columns and they're different colors. The green data is the data that I originally started with, and there's not a ton of it, right? So I'm showing from the World Bank pink sheets sort of commodity prices over time for different things. Everything else in the orange are areas in which I have added or feature engineered different columns to help our model begin to find patterns and information. Any lag that you have is essentially trailing an indicator. So either 1 month lag, 3 months lag, or six months and 12 months lag. So you have to see seasonality in there, and it starts to allow the model to pick up on these trends. Additionally, I added some dummy variables for some major events that you can take into account, which is COVID, the global financial crisis in 2008, and the Ukraine war, which we're sort of dealing with today. All of these different events sort of impact prices. Initially, the data went back from 1962. I cut it off to 1982, so the base year dollars on the Fed inflation calculation makes it easier. We're dealing with nominal dollars, but we do have the inflation calculation here. So the model can begin to predict and use those variables in its values and what it predicts. Here's the Fed inflation calculation. The big thing to take away here is that this is a real project with real data that's trying to predict real results in the future. The output of the data that we have goes all the way to 2024 of December. So the next month that we're going to predict is 2025, January 1st. But if you had more of the data, you could use it to predict that future next month, wherever you're getting that from your business or whatever elements that you have to track your prices. Now, I think it's important to understand a little bit about decision trees before we jump into this. This is from one of my college classes, a chart that I thought did a really good job of explaining what a decision tree is. You start off at this thing called a root node, which is the top, and then you have these sort of leaf nodes that go down. And essentially what you're trying to do is find a more homogeneous answer to the data. So when you go a certain route, you have some sort of degree of understanding that this is going to be what I predict. And when you read this, you start to say, this plus this plus this means that you are a class 0 for diabetes, meaning that you're not going to have diabetes. But if you change this to this, maybe you're changing it up a little bit as far as what your BMI needs to be, and it still says a class 0. But if you went this way and you have these sort of conditions, then there's a chance that maybe, yes, you have diabetes. I'm not going to go into all those details because not really my slides to create. I just thought I did a really good, or to share beyond this, I just thought I did a really good job of explaining how you read a decision tree. And that's important when we get into gradient boosting and what it's doing. Also, there's this statistics article on Geeks for Geeks that talks about entropy and how it's calculated. Entropy is what we're trying to solve. You're trying to have a lower entropy, meaning that you have more of a homogeneous mixture of elements and key points that direct you into where you want to go on the decision tree. Now, I'm not going to go into all the details on decision trees. It takes a long time to sort of really get intuition around this, but just understanding the basics of we're using decision trees for this, and there's this idea of entropy that we use to measure the mixture on each of those end nodes. Additionally, the documentation that we're using is open source, so you can install this on your own Python terminal. For me, I'm using Google Colab, but XGBoost is the model in which we're going to be using. Most of the cleaning's already been done, as I showed you before, so we're not going to spend much time on pandas or really clean anything, but mainly spend our time on working with the given data and the model. Anytime you have questions, you can go here. Definitely recommend if you have further questions and you need a tutor type environment, ChatGPT is always an outstanding resource to use it for learning, as well as YouTube videos and other tutorials that are out there. There's tons of information on this stuff. It's really about taking it all and being able to piece it together and then practically use it in a real life problem. And in this case, we're using it for procurement analyst type problems that might come up. Okay, so this next piece here is going to be really showing the model itself and how we work with it. So I did a whole markdown write-up around what this represents, and I'm going to post it along with the video. So if you want to dig into it deeper and really start to understand the nuance and the minute details of like why I did this and what it represents, check there. I'm going to go over and quickly review it because I want to keep this video relatively short in the grand scheme of things. So I've already done the introduction, so we aren't going to talk, well, we will talk about that for a little bit. Specifically first, this idea of decision trees. I talked about decision trees themselves and how you can pick a path and go to a final answer. Well, there's this thing called random forest as well, which is essentially a rebuild of that decision tree where you grab different sort of put all these tiles in a bag, some are blue, some are yellow, and you pull one out, grab the record, and put it back. And then that's going to essentially help you build out a new data set that you can run through another decision tree setup. That, in a sense, is like practicing an instrument again and again to get better at it. And it's a random forest. Now, if you're using gradient boosting, this idea is that you're doing the same thing, but you understand where your pain points are, and you're trying to improve those areas for the pain points. So think of it like playing an instrument and getting better, and then really practicing on that solo of the guitar that you're trying to practice over and over and over again, and eventually you get better and improve what that entropy score represents. Down here, we install the packages. I comment them out because I don't want to install anything that nobody else wants to install. So if you're using this, maybe just uncomment it before you run it, and then install the overall packages, which we'll talk to in this section of like what we're doing. So there's no point to really memorize that. Just know that these packages are what help us achieve and build out the overall model. If you're watching this video or you're trying to like follow along, I'm sure you're familiar with object-oriented programming. If not, maybe go back, understand those concepts first, and then come back to this video, and then you'll see how we use this object-oriented programming to help solve a very difficult problem. I talked about the data already, so we're good there. Just know that I loaded this into my Colab area, and I'm bringing it forward. And then I do a very little bit of cleaning. Essentially, I'm pulling out the date, the month number, because it's repetitive, the actual energy of the month in play, because we don't know that when we're trying to build out the next model and try to predict the value, as well as the calendar date. I pull out the calendar date because XGBoost is going to look at the year and the month, but it's not going to look at that sort of unique ID for a date in itself. It's not going to help the model get any better for our purposes. So we don't include that in the overall output. We grab a little bit of info on the data, and the output of this, you can start to see how our data is structured. Most of this is integers or float 64s, and there's a couple objects. These objects are important because those are categorical variables. In the future, you'll see what we do with those, because the model can't read a categorical variable like apple or banana. You need to encode that to an actual numerical output, so then they can use it to try to predict future values. And the same when you actually input data to predict, you need to sort of encode that as well, so it can take it in, ingest it, and then try to make a prediction. When we then we go ahead and build our training and test set. I'm just taking the first 80% as the train set and then the last 20% as the test set. Most of the time it would be a sort of a scattering and sampling throughout, but since I'm using time series data, that's sort of important for me and how I'm trying to use this. So I just essentially said at this given point, this is all training, this is how we're going to build our model. The remaining 20% will be test. And you can sort of see that layout here and sort of the changes in the values over time. This red line is where that split happens. Now you go ahead and build the pipeline, and essentially this is setting up a bin that you can put the elements inside and further tune them. So first of all, we encode the values that I talked about earlier with the apple and banana concept. And then you have this XGBoost regressor, which is sort of your boilerplate template. Now in here are the elements that you can adjust and tweak to make the model work better for you. We call this hyperparameter tuning. So the hyperparameters that we tune, I've listed out here in-depth details. But if you really want a sort of general understanding of what we're tuning, the idea is that we are making decisions on how deep on the decision tree we go, making sure that we don't overfit, penalizing things, and making sure that the number of samples in order to move forward are articulated so we don't go to the minute details and our model just ends up memorizing the entire pattern of our test data and doesn't actually solve anything for us in the future. That's a very important thing because with these decision trees, you can get very accurate scores on the training set. But when you go to actually put that against a real world test set, it doesn't actually work. So it's important to train it properly so you're not introducing bias and just memorizing the data, but you're actually building a model that can be deployed further into the future. We also do this thing called cross-validation, which is a folds. It allows you to use the entire value of your data to train it on, so you're getting more bang for your buck. Ultimately, what we're doing is we have 3 cross-validations, and we trial that with 361 different decision trees over 10 different iterations. So in total, when we build this model, we're running through 11,000 different trials to try to understand what is the best way to tune this model to drive the best value and provide the best output. And that's listed sort of here. Once we get all that trained and we've trained it up, you can sort of see the output and the decisions that the model used. Ultimately, we're only using 76% of the data every single time when we build each of these decision trees, which makes sense because we don't want to use every single column at every given time. We want to sort of use a portion of that. Otherwise, our decision trees all look the same. So you're sort of mixing and matching to make this decision tree the best way that it possibly can be built. And then ultimately, the best estimator is the same model. You can just use that in the future for future deployment of a given model. We use the root mean squared error to measure the accuracy of our model, and understanding that summary statistics is important, just like object-oriented programming is something to learn in this space. But the root mean squared error is determined in the same measure that your data that you're forecasting is being determined. And in this case, we're trying to determine what the future costs of materials are going to be, raw materials for steel. So this essentially is a look at that. And you have to put it in the negative sense because XGBoost is normally always higher is better, but with root mean squared error, lower is better. So when you do the inverse of that, you're going to get a more accurate measure. In this case, the result was negative 13.99. And what that tells you is our model was $13.99 up or lower than what our prediction really was. The output here shows a list of, a list is a tuple, but no, it's a list of the numeric values for that test set. So if we think back to this, these are the actual values that occurred. That list is essentially looking at that same time frame and trying to predict and say, this is what I think it is, or this is what I think it is not. I have a visual that shows that a little bit better, so it makes a little bit more sense. But these are the values that you care about because these are the values that you are predicting. Now, in order to make that a little bit easier on our predictions, let's go ahead and break it down a little bit further. So first and foremost, before we jump into the actual predictions, what columns had the biggest impact to our overall model. We have them listed here. It makes sense that it's the historical actual data and the lagging indicators that we built and feature engineered, as well as that sort of inflation factor I thought was interesting that it brought in from the FRED data as well, had an impact in what model and how the model is guessing what's going to happen in the future. And then ultimately, as I said, these are the predictions that the model's grabbing. We're only looking at sort of that right of the red line view here. And the red line is what actually happened. And this dashed green line is the predictions from the list that we called up here. I know that might be a little bit confusing, and hopefully I didn't talk too much around it, but that's how you can visualize the output. And the variance between here and here sort of can be depicted here. It's important to note that the RMSE for the actual use was about 3 times higher than what our trained data was on. But I think that's okay because you have instances like COVID, you have instances like Ukraine war, and a couple other instances that have increased that variance. Maybe we overfitted it a little bit. And you could probably make the model a little bit more conservative in the near term to reduce some of that. But I think for this case, it's probably okay. And then you go ahead and plug in the data for a future case of like what's going to happen in the future. And then you can get an output. So it's saying January 1st, 2025, the values, which it has no data, we have no data on, should be around $104.36. That's a powerful tool. It's a very powerful mechanism that you can use for your business. And you can't just use it for regression in dollars. You can use it for categoricals of yes, no's, true, falses, or trying to guess what something may occur. It is an amazing tool to get to one single value and build a model to drive this. Integrating this type of activity in your business, and whether you're a procurement analyst or contracting specialist or whatever, estimator, it's available to everybody today, and having the right people to help yield and wield this in your business is amazing. I know all the hypes around AI, and me myself, I get excited about that as well. But I think this, linear programming, prescriptive, predictive analytics are as powerful, if not more powerful in certain cases, than some of these most advanced technologies, and helping drive the business and make better decisions. So I know this is a lot. I covered quite a bit. Hopefully you stayed along for the whole way. Thank you for taking the time to watch and go through this with me. Additionally, go ahead, hit the link on the collab. I've made it available to everybody. Use it for yourself, copy it, and then build out another version for a problem state that you have, or ask me to help provide some inputs as well. Bring me in to help solve some of your hardest problems. Thanks again. I appreciate it, and I appreciate you letting me share these sorts of videos on some data science techniques in the real world.